Good morning, everyone. Thank you for joining my presentation on the applications of calculus in economic and geometry. My name is Wu Zijing, um, and today I will explore how calculus plays an essential role in various real-life scenarios, focusing on derivatives in economic and washing method in geometry and moments and the center of mass. Let's begin with an introduction to calculus. Uh, Calculus is a branch of mathematics that studies continuous change. It can be divided into two main branches: differential calculus, which focuses on rates of change and the slopes of curves, and the integral calculus, uh, which deal with the accumulation of quantities and the errors on the curves. Calculus is fundamental in numerous fields such as economics, engineering, physical, and more. Today, our objective is to understand how calculus is applied in real-world scenarios, specifically in um, economics and geometry. Our first focus is on the application of derivatives in economics. Derivatives are essential tools for analyzing and optimizing uh, various economic functions. The key functions we will discuss include cost functions, average cost functions, revenue functions, average revenue functions, perfect functions, and avenue perfect functions. Understanding these functions allows business to make informed decisions to optimize production, pricing, and also the profitability. Let's start with the cost functions and uh, average cost functions. Cost functions denoted as Cx. The Cx represents the total cost of um, producing units. For example, considering Cx equal to 500 plus 20x plus um, 0.5 x squared. This function includes fixed costs, variable costs, and quadratic costs associated with production levels. And about the average cost function, the AX. AX is calculated by dividing the total cost by the number of units produced. For example, AX ACX equal to 500 divided by x plus 20 plus 0.5x. This function helps business understand the cost per unit at different production levels. Using derivatives, we can find the marginal cost, which is the derivative of the total cost function. MC equal to uh, 20 plus x. Marginal cost indicates how the cost exchanges with each additional unit produced. It helps businesses decide whether to increase or decrease production based on cost implications. Next, we have revenue functions and average revenue functions. Revenue function Rx represents the total revenue from selling units. For example, Rx equal to um, 15x implies that each unit is sold at $15. The average revenue function, ARX, is calculated by ARX equal to RX divided by X. In this case, ARX equal to 15 indicates a constant revenue per unit. The derivative of the revenue function gives us the marginal revenue, MR, which is MR equal to the derivative of Rx equal to 15. Um, Marginal revenue helps businesses understand the additional revenue generated from selling one more unit. This information is crucial for pricing strategies and determining the optimal numbers of units to sell and maximize revenue. Then we come to the profit functions and the average profit functions. Profit functions are central to economic analysis. The profit function, Px, is defined as the differences between total revenue and the total cost, Px equal to Rx minus Cx. Using our previous examples, Px is equal to negative 0.5x squared plus 13x minus 500. The average profit function, APX, is calculated as APX equal to Px divided by x. For our example, APX is equal to negative 0.5x plus 13 minus 500 divided by x. This function provides insights into profit per unit at different production levels. The derivative of the profit function, the derivative of Px is equal to negative x plus 13, is used to determine the production level that maximize profit by setting the derivative of Px equal to 0. Solving this giving x equal to 13, indicating that the producing 13 units maximize the profit. And when the derivative of Px is bigger than 0, which indicates that the production increased the profit. And the optimal production level balance these challenges to maximize the overall profits. Let's do a deeper into the detailed examples of profit maximization. Suppose a company produce the productions with the following functions. The total cost function Cs is equal to 1000 plus 25x plus 0.75x squared. And the total revenue function is Rx equal to 16x. So the profit function is Px equal to Rx minus Cx is equal to negative 0.75x squared plus 35x minus 1000. And the first derivative of the Px is negative 1.5x plus 35. And the critical point is nearly the 23. Therefore, the optimal production level is approximately 23 units for the max profit. So for decision making, it helps businesses determine the most profitable production level, and for resource allocation, it ensures efficient use of resources by avoiding overproduction or underproduction. And for strategic planning, it informs long-term business strategies for growth and profitability. And the washer method is a technology for finding the volumes of soil of revulsion by integrating the areas of washer across the interval of revolution. The formula is listed here, and it can be applied in engineering designing, manufacturing, and architecture. Let's do an example. To calculate the volumes of a soil rotated about the x-axis. First, we identify the radius. The outer radius is Rx equal to Rx, and the inner radius is Rx equal to 0. And put it into the formula and calculate, finding the volume is 8 pi. And the next example, the volumes of a hollow pipe. It is to calculate the volume of a hollow pipe with an outer radius of 5 and inner radius of 3 and the heat of 10. First, we are defining the radius and heat. Outer radius is 5 and inner radius is 3 and height is 10. Then set up a volume formula and perform calculation. And the volume is 116 pi. Finally, let's discuss the moments and the center of mass. Fundamental concepts in physics and engineering that describes the distribution of mass within objects. The moment is a measure of the distribution of mass relative to an size. It helps in understanding how mass affects the balance and stability of an object. And the center of mass, it is the point at which the entire mass of an object can be considered to be concentrated. It is the balanced point of the project. It is essential for designing balanced structure, analyzing rotation dynamics, and ensuring stability in systems. Let's consider the center of mass of an object with radius r and the uniform density rotated about the x. Due to the symmetry about the y, the x bar is equal to 0, and then calculate the y bar. Then use polar coordinates for integration. Convert coordinates and calculate. Thus, x bar is L divided by 2 and the y bar is 0. So we can find out the center of the mass. So understanding the center of mass is crucial for balancing objects and designing stable structures. Then we come to the next example. Consider a uniform thin rod of length along the x. The center of mass lies at the midpoint of the rod, and it can ensure balance when the rod is supported at this point. And the third example is to explore the center of mass of a composite objects made of two rectangles. The first rectangle, its width is 4 and height is 2 and mass is 6. The second rectangular, whose width is 2 and height is 3 and mass is 4. So we can use the formula to calculate the total mass is 10 and the center of mass is at 3.6 and 1.2. It is useful in designing composite structure to ensure overall balance and stability, and facilitates accurate placement of supports and balance points in engineering applications. In conclusion, calculus is integral to various real-life applications. particularly in economics and geometry. We explore how derivatives aid in optimizing cost, revenue, and profit functions in economic, the virtual method for calculating volumes of sorts of revolution in geometry, and the concept of moments and center of mass in physical and engineering. Understanding calculus not only enhance our problem-solving skills but also enable efficient decision-making and innovation across diverse fields, whether it is optimizing business profits, balancing market forces, designing complex engineering structure, or analyzing physical phenomena. Calculus remain a process. So, continue exploring the application of calculus to unlock new chance and drive advancements in our respective areas. Thank you for your listening.